Okay, welcome back. So this is section 17.6, subsection 2, I guess. Series and integrals as linear combinations. I like the exposition of the book, but I am going to jump into the whiteboard and kind of give my own explanation of what's happening here, and then I'll reference the book maybe when I finish that, because I guess I've decided to like my explanation better. But what I'm going to throw out to you is just a couple things, and I want to see if you can kind of start to see the pattern here. So let's start with x1, x2, x3 as a vector in R3. And let e sub 1 be 1, 0, 0, e sub 2 be 0, 1, 0, e sub 3 be 0, 0, 1. Now these are really the x, y, and z vectors that you're used to with the hats over them, but I'm using a different notation, and you're going to see why in just a little bit. Then let's call this x vector on the left truly the x vector. Then the x vector is equal to the sum from j equals 1 to 3 x sub j e sub j. And I think you will all agree with me once you take a little bit to kind of digest what this sum is actually saying. So the sum is saying start at j equals 1 and write out that term. That's x sub 1, e sub 1. Move to j equals 2 and write out that term. That's x sub 2, e sub 2. Move to j equals 3 and write out that term. That's x sub 3, e sub 3. And I think you all agree with me that if we reinterpret e1, e2, and e3 as the x, y, and z vectors, or just by their definitions above, this becomes x1 because that's on the e1 vector, x2 because that's on the e2 vector, and x3 because that's on the e3 vector. Okay, but let's jump ahead to an infinite dimensional setting. Say something like the x vector is now equal to x1, x2, x3, ... and just suppose it goes on for infinity. Now I'm going to use little l2 here, little l2 of n. Don't worry about that notation, but that's the notation I'm going to be using here. And we're going to let just the same idea, e1, now be 1, 0, 0 with some dots. It's infinitely long. e2 is 0, 1, 0 with some dots. e3 0, 0, 1 with some dots. Now I can put some more dots here. Say e sub n is a bunch of zeros, but then there's a 1 eventually. And that 1 occurs exactly at the nth term, or the nth entry. And everything else is zeros. And I think you all would agree with me on that will form a basis. And I think you'll all agree with me as well that we have something like the x vector is still the sum j equals 1, but now the top here, that's my dimension, right? So if I'm in an infinite dimensional space, I have an infinite series, and I recover x sub j, e sub j. And this would just be the exact same as before. It's x1, e1, plus x2, e2, plus, and so on. And it just so happens that this goes on infinitely far, right? X sub n, e sub n, plus, and so on. And it just keeps going. But eventually that does fill out the vector of x. And we can generalize these notions with inner products as well. So let's think about inner products in finite and infinite dimension. And we have something like the inner product of two finite dimensional vectors, let's say x1, x2, x3, inner product y1, y2, y3. And that is equal to, traditionally, x1, y1 conjugate plus x2, y2 conjugate plus x3, y3 conjugate. But now I'm going to represent this as a sum. J equals 1 to 3, xj, yj conjugate. And in infinite dimensions, I'll jump over to the red color here. In infinite dimensions, x1, x2, x3, dot, 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 y1, y2, y3, dot, dot, dot. Their inner product in infinite dimensions can be written as x1, y1, conjugate, plus x2, y2, conjugate, plus dot, 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 plus maybe the nth case, plus dot, 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 which I can represent that as a series as well. J equals 1 to my dimension, which happens to be infinite here, x sub j, y sub j, conjugate. Okay, so that's maybe how we would jump to inner products in infinite dimensions, as well as we were representing our vectors in infinite dimensions. But the question is, so these in these infinite dimensions, the infinite dimension above is indexed, this is a fancy math word we use, indexed by the natural numbers n being 1, 2, 3, and so on, and that's why we see 1s here, 2s here, we would see 3s, and so on, right? That's a natural number, whatever that n is. So we say it's indexed by the natural numbers. The big question becomes, can we do the same thing but with an index of 0 to L? That's an interval, right? It's an interval of real numbers. Can we talk about the same behavior with an index of an interval instead of an index of a natural numbers? Now, notably, it's still infinite dimensional because the index, right? The index right there, there are infinitely many numbers inside of 0 to L. But what we do is we represent things differently, right? Our inner product now becomes x, and it's indexed by some element in, and maybe I won't use x here because I would like to say x is in 0 to L. I'll say phi, and it's indexed by some element x, and psi, and that's indexed by some element x as well. Keep in mind, x is in 0 to L. So for each x in 0 to L, there's some number phi, and there's some number psi, and both of those are indexed by x. And I'm going to sum them up. I'm going to say phi sub x, psi sub x, overline, and this is going to be the minimum x, plus the next x, plus the next x, plus the next x. But there's infinitely many of these x's, and what does it mean to be the next one? Well, there's an infinitesimally small distance between any two x's. So I have so many of these terms that, what does it mean? Maybe in calculus terms, what would x sub next be? This is x plus dx. That's what x next means, x plus dx. And then we would have x plus 2 dx and x plus 3 dx and so on. And in fact, if we're adding up infinitely many of these, each of these have to be multiplied by an infinitely small quantity dx. And what is the sum of an infinitely many numbers of infinitely small quantities? This is precisely the integral of phi sub x, psi bar sub x dx from 0 to L. And of course, rather than writing subscripts in mathematics, these here are just functions. This is phi of x, psi bar of x dx. This is why we have this as our inner product of phi and psi in L2. It's because we're doing the same procedure that we did before with all of our other situations, except we're now indexing our functions over an uncountable set instead of a countable set, right? So Riemann sums at the end of the day, which produce integrals for us, are sums. So integrals and sums are the same thing. It's just with integrals we have kind of an uncountable number of entries versus in sums we have a countable number of entries. And you don't have to worry about that word countable or uncountable. It just means that we're kind of dealing with different versions of infinity. And one of them we index over the interval 0 to 1, and all of a sudden that gives us this inner product that we're starting to get used to on functions now. So if we have something like that for functions, let's jump back to the basis. What does it mean does it mean to have a basis over maybe this interval 0 to L, right? What would a basis look like in that case? And this gets a little bit tricky because the way I'm going to represent it is not the way that the book's going to represent it. So our natural, if I take this E sub n, which was my infinite vector of zeros, and then a 1, and then some more zeros, where the 1 was in the nth place, and I reinterpret this indexed by x now. This is the function. I'm going to call it chi sub x, where I'll call it chi sub x sub 0. It's a function of x, which is piecewise. It's equal to 0 if x is not equal to x naught. It's equal to 1 if x is equal to x naught. And what that means is, similarly to how we were able to represent maybe this vector x, which was like x1, x2, dot, dot, dot. The vector was the sum j equals 1 to infinity, x sub j, e sub j. Now we have a similar idea, but for functions, my function phi can be represented as the integral from 0 to L of let's say phi of x chi of x naught x dx. And this is phi of x naught. And in fact, there's a dx over here as well. If I want to get rid of the dx's, what I can do is I can reinterpret this as an infinity. So if I want to get rid of the dx's, instead of putting a chi here, I put a delta here. It's the lowercase delta, and that becomes infinite. Really, it's 1 divided by dx, and I have a delta sub x naught there, and that is how I could represent a function as an integral the same way I represent this vector as a sum. So that's kind of where we're headed in this class. This is the overarching idea. Now let's jump back to the book and see what that's saying. Okay, so I've jumped to subsection 17.6.3 here because point 2 is basically what I was saying, just in a lot less detail. And so when we jump to 17.6.3, we're jumping to now projections. And it turns out that we can represent projections in an infinite dimensional setting using an inner product, psi of x, maybe that's capital psi of x, against lowercase psi sub n of x dx. And since that is an inner product, it produces the coefficient a n of a projection. This is saying how much overlap does any specific psi of x have against another one, maybe indexed by n. And if I jump down to the example is why maybe we care about this, because if we look at this function f, which is a triangle wave, so it looks something like this, where that's 0 and that's L. So it just looks like a triangle by itself. We can actually decompose it by projecting onto the signs. So let's project this triangle onto a sign, which let's recall what the sign looks like over that interval as well. Sign's going to look something like this. Triangle looks like this, 0 to L, 0 to L. That's for n equals 1. For n equals 2, we have something like this. For n equals 3, we have something like that, and so on with the signs, and we can project onto each one of those using the standard inner product notation. And in doing so, we recover, all the way down here, the inner product of f, which with each of the signs gives me a projection coefficient which looks like the following. It's a little bit ugly. I'm not entirely happy with this example because of how ugly it is, but if I compute the inner product of my triangle wave up top, there at the top, and I compute the inner product of psi, I recover the following numbers, where if I actually plug some n's into those numbers and take some sums here against those, I'm basically looking at the projection onto the nth entries, and I'm scrolling all the way down. So this is the projection in blue onto the first sine wave. This is the projection onto the fifth, all the way up to 5 sine waves. the projection onto 20 sine waves, and so on. This is hinting once again at the Fourier series, which we'll get to eventually. So I don't worry too much about it for now, but basically what we can do is we can perform projections of functions where you can then reconstruct a function using finitely many basis elements, or an approximation using finitely many. Anyway, that's all I have for you today. I'll see you in class. Bye.